Welcome to the Deep Dive, where we get into the weeds of important technical papers. Today, we're looking at something I think many of you, our technical audience of engineers and researchers, will find really interesting. It's a paper called ColorAgent, Building a Robust, Personalized, and Interactive OS Agent. And it's a joint effort from Shanghai Jiao Tong University and the OPO Research Institute. Our mission here is to really unpack how they built this OS agent. We're talking about tackling complex, long tasks on your device, but maybe more importantly, shifting the agent from just a functional tool to something more like a collaborative partner.
Yeah, exactly. I think that shift is the core idea. They're moving away from the OS agent as just a passive task executor, which can feel pretty cold and utilitarian towards, as they put it, a warm collaborative partner. That's a big ambition.
It definitely sets a high bar.
Oh.
Okay, so for listeners needing the quick version, the highlights right up front, what are the key technical innovations driving this?
Well, there are really two main thrusts. First, architecture-wise, they've built this quite sophisticated multi-agent framework. This isn't just one monolithic model. It has specific modules to handle generalization, consistency, and, crucially, error recovery. We're talking knowledge retrieval, task orchestration, and hierarchical reflection modules.
Okay, a modular approach.
Yeah.
The second part.
The second part is the training. They developed a custom two-stage training process. It starts with stepwise reinforcement learning, focusing on single, good decisions, and then moves to something called self-evolving training, which is designed to build robustness for those long, complex tasks in the real world.
And did it work? What are the numbers?
The results are pretty impressive, yeah. They achieved state-of-the-art success rates on some tough dynamic Android benchmarks. We're talking 77.2% on AndroidWorld and 50.7% on AndroidLab, so definitely pushing the envelope.
All right, solid numbers. Let's zoom out a bit first. Context is everything, right? We've seen human OS interaction evolve massively, command lines, GUIs, now AI assistance is becoming common. The big vision seems to be this persistent, context-aware agent managing our devices.
Exactly. But the challenge with an OS agent, compared to, say, a web agent, is fundamentally different. Traditional agents often handle isolated tasks, book this flight or summarize this page.
Right, self-contained things.
Yeah. An OS agent, though, has to handle potentially very long sequences of actions across multiple apps within a constantly changing environment. The user's intent might evolve, or it might be vague to start with.
That brings us back to the cold tool versus warm partner idea.
Precisely. A simple tool breaks easily. If you just tell it, order a hamburger, a basic executor might just grab the first option.
Which is probably not what I wanted.
Right. The partner agent, the color agent they're aiming for, needs the intelligence to either check your history, you usually get the spicy one, or, crucially, ask, hey, which specific hamburger did you have in mind? That interaction, that personalization, that ability to handle ambiguity, that's the goal.
Okay, let's dive into how they build that robustness. The foundation seems to be this two-stage progressive training. Stage I, stepwise reinforcement learning. What's happening there?
So stage I is all about nailing the single-step decision-making, making the right click or swipe at the right time. And interestingly, they didn't go with the standard reinforcement learning algorithm, PPO, proximal policy optimization.
Oh, why not PPO? It's pretty common.
It is, but PPO can be quite complex to tune and computationally heavy, especially with the kind of data you get from GUIs.
Yeah.
It often needs a separate critic model to estimate value functions, which adds overhead.
Okay, so what did they use instead?
They opted for something called Group Relative Policy Optimization, or GRPO. It's designed to be a lighter weight alternative. Instead of a complex critic, it estimates the relative advantage of different actions by looking at groups of responses from the model. It's generally more stable and efficient for this kind of task.
Makes sense. Efficiency matters when dealing with potentially massive UI state data. Now, rewards in RL are always tricky. How do they balance getting the action right versus, say, making sure the output text description was perfectly formatted?
They use a combined reward. There's a reward for accuracy, for SES, did it perform the correct action, and a reward for format adherence, for FNT dollars. But they weighted accuracy much higher. The final reward formula gives about 4 times more importance to getting the action right. Alpha dollars in 2.2 means 80% weight on accuracy, 20% on format.
So prioritize doing the right thing even if the explanation isn't perfectly phrased.
Exactly. Function over form, initially.
Now, the data they use for this RL stage, it sounds like they put a lot of thought into constructing it. Tell us about this multi-path augmentation.
Right. This is really key for real-world robustness, I think. They recognize that on a real phone, there are often multiple ways to do the same thing. You might swipe down to go back, or tap the back arrow on the screen, or maybe even use a system-level back command.
All achieving the same result.
Precisely. So simply training on one canonical path makes the agent brittle. If the UI changes slightly, that path might break.
So they trained it on all the valid ways.
Yes. They used a large vision language model to help identify these equivalent actions in their training trajectories and then assign them all equal reward weight. This forces the agent to learn flexibility. It might not score perfectly on a rigid benchmark that only expects one specific path, but it's much more likely to succeed out in the wild.
That's a really interesting trade-off. What about difficulty-based filtering? Sounds like they were selective about the training data.
Yeah, this is about training efficiently. They ran their base model on the data first, multiple times, to see how consistently it could solve each step. If the model got it right every single time or failed completely every time, they actually discarded that sample.
Why discard the easy and the impossible ones?
Because they're not very informative for training. The easy ones are already learned, and the impossible ones might just be noise or too hard at that stage. They focused the RL training on the boundary cases, the steps where the model was uncertain, sometimes succeeding, sometimes failing. That's where the learning potential is highest.
Smart. Okay, that covers stage 1, building solid single-step actions. But OS tasks are long, complex chains. You hit a data bottleneck pretty quickly for those kinds of trajectories, right?
Yeah.
Is that where stage 2, self-evolving training, comes in?
Exactly. Stage I gives you the building blocks, but you need data for long, multi-step interactions across apps. Stage 2 tackles the scarcity by having the agent essentially generate its own training data. It's an iterative loop. Use the current model to generate task attempts, filter the successful or interesting ones, use that new data to improve the model, rinse and repeat.
Generate, filter, optimize, repeat. How do they kickstart this? And how do they ensure the generated data is actually useful and not just noise?
Good question. They start with a set of seed queries. Some are high-quality examples crafted by humans covering core functionalities. Then they use a powerful large language model, DeepSeek R1 in this case, to expand on these seeds, generating lots of variations, different phrasings, and importantly, corner cases that humans might miss.
Okay, so you get diverse starting points, then the agent tries to execute these.
Right. The rollout phase happens in both Android virtual environments and on actual physical ColorOS devices. They use a high temperature setting during generation, which encourages the model to explore different, sometimes non-optimal paths. Diversity is key here.
But diverse paths could also be wrong paths. How do they filter?
That's the crucial filtering step. They have a suite of specialized discriminator models that check each generated trajectory along 5 axes. Did it actually complete the task? Were the individual actions valid? Was the path taken relevant to the goal? Was the internal reasoning coherent? And was it efficient, or did it have redundant steps? Only trajectories that pass these checks get added to the training set.
So it's a pretty rigorous quality control for the self-generated data.
Very much so. It ensures the model learns from productive exploration, not just random wandering.
Okay, that makes the training approach much clearer. And it also highlights why just having one big model, even well-trained, might not be enough. Their own analysis showed failures due to generalization limits, reflection issues, inconsistency, which neatly leads us to the multi-agent framework.
Absolutely. The training builds a capable core execution module, but the multi-agent framework adds layers of specialized intelligence around it to tackle those specific failure modes they observed. Think of it like the core agent is driving, but it has navigators and mechanics helping out.
Let's break down those helpers. First, knowledge retrieval. How does that help with generalization?
This module acts like an external knowledge base lookup. When the agent gets a task, this module can retrieve relevant information, KKAPI, from a database dollars. So, if the task is mark my urgent tasks, the knowledge retrieval module might fetch the fact. In the Tasks app, red color signifies high priority.
So it provides context the agent might not inherently have.
Exactly. It grounds the agent's actions in specific app knowledge or conventions, making it much better at handling tasks it hasn't seen in exactly the same way before. Less guessing, more informed action.
Okay, next module, task orchestration. This tackles consistency and memory for longer tasks, right? How does it prevent the agent from forgetting what it did 3 steps ago?
Right. So first, it has a task classifier that looks at the user's goal and decides if it's a simple single task or a complex one that needs to be broken down into smaller steps, GG dollars, G2 dollars, and so on.
Decomposition. Makes sense.
Then, crucially, after each subtask G dollars is finished, a task extractor analyzes the trajectory, the sequence of screens and actions, and pulls out the essential information. Maybe it's the final confirmation number or the name of a file saved, like expenses.jpg.
Okay, it extracts the key result.
Yeah. And then a task rewriter takes that extracted information and integrates it into the instruction for the next subtask, GTK plus $1. So the next step starts with full awareness of what just happened. It's like passing notes between steps. That's the memory transfer piece.
That's clever. Continuous context. And the third helper module, hierarchical reflection for error recovery.
Yes, this is the safety net designed to catch problems before they derail the whole task, and it works at multiple levels, hence hierarchical.
What are the levels?
There's the action reflector, which is watching in real time. It compares the screen before an action and the screen after to see if the action had the expected effect. Catches immediate grounding errors, like clicking the wrong button.
Okay, step-by-step checks.
Then there's the trajectory reflector. This looks at slightly longer sequences, maybe 3 to 5 actions, checking if the sequence makes sense together, if it's coherent and moving towards the goal efficiently.
Kind of a local sanity check.
Exactly. And finally, there's the global reflector. This one only activates when the agent thinks it has finished the entire task. It does a final assessment. Does the end state actually satisfy the original user request?
So multiple layers of self-correction. The paper had a great coffee ordering example that pulls this together. User says, I would like a cup of Americano. How does the system handle that?
Right. You see the modules collaborating. First, knowledge retrieval might kick in. Okay, ordering coffee usually means using the My2On app on this device, so it navigates there. Then, maybe during navigation, it clicks the wrong shop link. The action reflector or trajectory reflector catches it. Hold on. The screen shows Cuddy Coffee, but the goal mentioned Luckin Coffee. Need to go back. It self-corrects.
Immediate error fixing.
Yeah. And then comes the partner aspect. Before confirming the order, the system might access user history or preferences. This is the personalization layer interacting. It finds, historical data shows this user nearly always prefers iced coffee.
So it overrides the default.
It proactively changes the order from the default hot to ice, aligning with the likely user intent, even though it wasn't explicitly stated. That's moving beyond literal instruction following to anticipating needs.
That really illustrates the warm partner idea. Let's talk more about that personalization, the second major pillar. How does it work when the agent have user history?
When it has access to memory past interactions, user profiles, they use a framework they call personalized user intent recognition. It leans heavily on retrieval augmented generation, or AGG.
Again. How is it applied here?
It retrieved 2 kinds of knowledge. First, explicit knowledge like standard operating procedures, essentially common successful paths for tasks the user has done before. Second, implicit knowledge user habits, preferences, maybe inferred from patterns over time.
Okay, explicit SOPs and implicit habits.
Right. And the RAG model takes the current user query and this retrieved knowledge to rewrite the query into a more personalized, specific instruction for the execution agent. It's aiming for much better alignment with what the user actually wants based on past behavior.
But what about new users or situations where the intent is just plain vague, like our order a hamburger case? How does it decide whether to just guess or ask for help when there's no history?
That's handled by what they call proactive engagement, specifically designed for these low confidence or ambiguous scenarios. They use a clever 2-stage learning approach here.
2 stages for asking questions.
Sort of. It decouples learning when to ask from learning how to act once an answer is given. The first stage learns to predict whether the situation requires clarification, essentially, deciding to output an ASK action instead of a regular UI action.
Okay, so it learns confidence thresholds, basically.
Yeah, or identifies ambiguity patterns. The second stage then learns how to correctly execute the actual task action, the non-ASK action, after the user has provided the clarification prompted by the ASK action. This stops the agent from just blindly pushing forward when it's uncertain. It knows when to pause and ask.
That sounds much more robust. And do they test this interaction quality?
They did. They used specific benchmarks designed to measure this kind of human-agent interaction and intent alignment, like Mobile IRR and Varios Bench. And they reported state-of-the-art results there, too, like a 58.66% intention alignment rate on Mobile IRR and almost 69% success on Varios Bench. It suggests these modules are genuinely helping bridge the gap between command execution and understanding true user intent. And just to reiterate those main benchmark scores we mentioned earlier, 77.2% success on AndroidWorld, 50.7% on AndroidLab, pretty strong performance. But beyond the headline numbers, there was a really fascinating technical insight from their ablation studies.
Ah, yes, the part about model size versus the framework.
Exactly. They compared their full system using a fine-tuned 32 billion parameter model against using a much larger 72 billion parameter model as the core agent.
And you normally expect bigger is better, right?
You might think so, and interestingly, the larger 72B model actually achieved a higher reward during the training phase. It learned the training data, the specific trajectories really well.
Okay, better training fit.
But, and this is the key part, when they tested these models on the dynamic unseen tasks in AndroidWorld and AndroidLab, the smaller 32B model, when combined with the full multi-agent framework, retrieval, orchestration, reflection, significantly outperformed the giant 72B model. That's where the 72% came from.
Right, so the smaller model plus the smart framework beat the bigger standalone model.
Decisively. It strongly suggests the 72B model, despite its size and better training fit, was more prone to overfitting the specific training data. It didn't generalize as well to the dynamic nature of the real OS environment.
That's a critical point. It implies that for these complex interactive tasks, simply scaling the base model isn't the whole story. The architectural components, the reflection, the orchestration are providing huge value for robustness and generalization.
Absolutely. It suggests that engineered robustness through these complementary modules might be more effective, or at least more efficient, than just throwing more parameters at the problem, especially in dynamic environments.
Okay, so ColorAgent shows a promising path forward. But what are the big roadblocks still ahead? What did the researchers themselves identify as the key challenges to actually getting these kinds of agents into widespread practical use?
They highlighted three main areas. First is the evaluation paradigm. Current benchmarks, like AndroidWorld, are good starting points, but they're still relatively simple, limited apps, fairly straightforward tasks. They argue we need benchmarks that better reflect real-world complexity and, importantly, measure user-centric aspects.
Beyond just task success rate.
Yeah. Things like, how accurately did it capture the user's intent? How well can the agent evolve on its own? What's the actual user experience quality? We need richer metrics.
Makes sense. What's the second challenge?
Agent collaboration. Their multi-agent framework is one approach, but there's a whole design space to explore here. How should these modules interact? Centralized control, sequential pipeline, maybe a fully connected mesh. And we need to understand the trade-offs. Does tight collaboration limit the autonomy of specialist agents? Does it create communication bottlenecks?
So optimizing the internal teamwork of the agent system. And the third, I suspect I know this one.
Yep, security. Giving an AI agent deep control over your operating system is obviously a huge security consideration.
Understatement of the year.
Right. So this needs serious work. We need robust sandbox environments to limit potential harm. We need much better ways to handle unexpected errors or even potentially malicious inputs or scenarios. And critically, we need very fine-grained permission controls. The agent needs clear boundaries on what it can and absolutely cannot do.
Safety, controllability, boundaries. Absolutely critical. Okay, let's wrap this up. If we distill this deep dive on ColorAgent, the key takeaway seems to be that building a truly robust and helpful OS agent isn't just about one thing. It's the synergy.
Exactly. It's the combination. Powerful training techniques at Stepwise RL for grounding, plus the self-evolving training for complex data, combined with a smart modular architecture using knowledge retrieval, task orchestration, and hierarchical reflection. That's what seems to bridge the gap from brittle tool to something approaching a reliable partner.
A partner that's not just effective, but also aligned with what you actually want.
And that alignment, that partnership quality, might be the most interesting challenge going forward. If the ultimate goal really is this warm, collaborative partner, then maybe we, as a research community, need to think beyond just task success rates.
What kind of metrics are you thinking?
Well, how do we measure things like user trust in the agent? Or its ability to correctly interpret truly ambiguous requests, or even quantify its capacity to learn and adapt over time, its self-evolution potential, shifting our focus towards measuring the quality of the partnership, not just the completion of tasks. That feels like the next big frontier here.
That's a fantastic point to ponder. Measuring partnership, not just performance, really gets you thinking. If you, the listener, want to dig into the specifics of GRPO or see how they structured those agent modules, the researchers have made their code available. You can find it on GitHub at https://made-agents-mobile-use.
Thank you for joining us for this deep dive into ColorAgent. We hope it was insightful, and we'll catch you on the next one.